All right, so a couple things. First off, when we do this problem, um, uh, on page 224, they talked about how the projection onto the x-axis would be this guy. Okay, if you think about it, it makes perfect sense because whatever you have for an x component is all that's going to show up. You have 1 times x plus 0, and all you're going to have is the y is going to have 0. Sweet. So if I want to project onto the y-axis, I was correct when I said it should be this and this, which will give you this and this. Okay, now we'll talk a little bit more about where that comes from. But check it out. Now, Jay screwed the pooch on this the first time, and I couldn't figure out what he was doing wrong because whenever I'm chosen to do something, all right, 1, 1. All right, cool. That's great. Now, let's rotate this 45 degrees. Oh, what? Now, where is it? Oh, it's 0, 1. Wait, if I project that onto the y, dude, it's already there, you ding dong. Oh, what? Now, if you rotate 45 more, what do you get? You get the same vector. You get the same vector, and it's kind of annoying because it's still 1 unit long, and you're like, what's going on here? Because when I rotate this over to here, when I rotate it over to here, and then put it down onto there, so yeah, it messed me up, and I was getting freaked out and annoyed by myself. So what I picked out this time, let's just pick out a random different one. 3, 1, 2. Okay, here's our vector 3, 2. Now I figured this out. This is 33 degrees. Not percent, you jackass. 33 degrees. Okay. Now I'm going to rotate that 45 degrees because I feel like it, like the one in the book does, which means this is going to be 78 degrees here in a jiffy. We're going to double check ourselves on that. Okay. Then, whatever this point is, we're going to rotate it. We're going to come straight in, meaning that it's going to be 0, comma, whatever the y value. This is x, y. I'm going to end up with 0, comma, y, which is going to be a shorter vector, obviously, than it was previously. Yes? Now I'm going to rotate that shorter vector over 45 degrees. And so I'm going to be able to, obviously, these are going to be the same x and y point, like 2, 2, 4, 4, whatever it happens to be. Note that this vector here is the same as this one, which is shorter than this one, which is the same length as this one. So in a few minutes, we're going to make sure that that's true. So let's see what happens. So let's start off with our 3, 2. And let's multiply that by the rotation matrix. Now, I happen to know the decimal form of this is this, and this is the sines and cosines of 45. Approximate. Okay, so I do that. I get, did it appear somewhere? I got 0.707, comma, 3.53. So that means this point here is, actually looks a little more like this. Okay, where this is the same length vector here as this guy here is. It's just been that's rotated 45 degrees. And you're like, I don't believe you, Jay, that it's 78 degrees. Well, let's check it out, bro. So what I did was I took the inverse tangent of 3.5 over 0.707. I get 78 degrees. How about that? Huh? How about that? Now, if you times that out, you're going to get 0, 3.5. In other words, we're just going straight sideways. Cool. And then let's take that and let's take that value here. And let's project it onto the y-axis. Okay. And then let's take that guy and hit it with the rotation matrix again. And you will get, you will get negative 2.5, comma, positive 2.5. Oh, I forgot. Yeah, they actually negative, but they're the same value. Now, what's the magnitude of this? Well, the magnitude of this guy is the square root of 12.5. What's the magnitude of this guy? The magnitude of that guy would be the square root of 13. Again, this is a longer vector than this one, because when I projected it onto the y-axis, I lost the x-coordinate length. Therefore, of course, it's going to be a shorter vector. Okay. Now, The link that was in the lesson takes you to this website. And suffice to say, the projection, we're going to do the projection of U onto V. And suffice to say, this is what it comes out to be, is this. Now, you can read through that a little bit more. Suffice to say, though, this is the game, and it's just doing some multiplications, moving a few things around. Now, the difference being is this. These are vectors. So this is a 2 by 1 times a 1 by 2. That's going to give me a 2 by 2. That's, in other words, that's a matrix on top. On the bottom, it's a 1 by 2 times a 2 by 1. This is a dot product on the bottom. In other words, it's a scalar. Meaning I'm going to be left with a projection matrix. So in our case, if we're going to project it onto the y-axis, and you can do it either way you want to, because remember, this is just the magnitude of this guy, the magnitude of it squared. So it doesn't really matter. I'm going to choose 0, 1, 0, 1. And then on the bottom, I'm going to have 0, 1, dot, 0, 1, which of course is just 1. On the top, you're going to have 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. Hey, there's your projection matrix. Cool. Does it work for any vector that you want to project onto? Absolutely. Let's say you want to project onto 3, 1 for whatever reason. Okay, weirdo. If that's what you want to do, then you're going to take 3, 1, 3, 1 over, and then you get 3, 1 dot 3, 1. So that's going to be 10 on the bottom. And then it's going to be, excuse me, 9. Because it's just row times column, right? So 3 times 3 is 9. 3 times 1 is 3. 1 times 3 is 3. 1 times 1 is 1. So that means you're going to get 0.9, 0.3, 0.3, 0.1. Okay. Let's see what that looks like. Okay. I'm just going to check one thing here real quick, and then we'll get it going here. Okay. So let's do this here. Let's take a vector. Let's pick a vector. Let's do our 3, 1. This is the one we're going to project onto, like so. Let's take what the heck? Let's go crazy here, dog. Let's do this one. What? Let's go -4 clearly. -4, 3 will be my vector. So I'm going to project this guy onto this guy here. Now, clearly, it's going to be some vector going this direction, obviously, right? So let's see what our projection matrix looks like. Now, remember, the projection matrix is all about V. It's all about V, okay? So I'm going to take this projection matrix, 0.9, 0.3, 0.3, 0.1, and we're going to multiply it times our vector. So our vector should end up looking like this. Are you with me? It should end up down here like this. Let's see if that's true. Okay. Gosh, it's too late in the day to do some actual math. So I'm going to use the calculator. I'm just not feeling it. I'm just not feeling it, man. I don't feel like it. I feel like. And then, oh, you jackass. Come on. Semicolon. Add a babe. You got this, Jay. Sorry, I had to have some affirming self-talk. -4, semicolon, 3. Look at that. Now, oh, jackass. Oh, look at that. I hit 0.4 instead of -4. Of course, you already saw that. What? -2.7. Wait for it. -0.9. What? Now, Jay, could you prove this to me? I think so. Let's go into Geogebra, and again, only because I think it's helpful. Geogebra, geometry. There you go, babe. Geometry, whatever. Uh-oh. That is not what I wanted. Here, give me the classic. Oh, fiddle faddle. Here, back out, back out, back out. There you go. GeoGebra Classic. Okay, here we go. Judas Priest. Okay, here we go. So clearly I'm in this graphing deal. So I can just go in like this, and let's see what happens here. So I'm going to put in my original vector, which was the point, which was the vector rather. What was my vector? My vector was -4, 3. Let's go ahead and put that on there. So I'm going to put that in as a vector, which is this guy here. And I'm just going to drag it like so. Oopsie daisy. Oh, shoot. Undo, undo, undo. Holy buckets. All right, so I'm just going to click on this. -4. 3 is right here, yes? Boom. Sweet. Now I'm also going to project the other vector, which was 3, 1. See if this makes sense to us. So over 3, up 1. Boom. Nice. Now I'm going to go ahead and show the projection matrix, which we said was -2.7 and -0.9. So the way to do this is just go ahead and grab another vector. Check this out. You're going to see what I mean. And you're like, well, you can't get exactly what you want. You can't always get what you want. Yeah, it's right. But what you can do is go in here and edit these. Bam. Bam, I said. Bam. All right, there it is. Sweet. Now, you're like, are you sure that's correct, Jay? I don't know, but I do know this, friend. I could take a line and go from hither to yon, bloop, and that should make a right triangle when I project it, yes? Let's see if that's true. See if I can do it right. Watch, you have 2 ways to go, and, oh, look at that, I guessed right. How freaking weird is that? Bam! 90-degree angle, friend. Again, so, if you come back over here, okay, it's this up on top, so it's V transpose over V transpose V. V transpose V on the bottom is the dot product. On the top, you're just going to make yourself a matrix. Now, can I do that in the calculator? Yeah, actually you can. So what a guy can do is, for instance, let's just come in here and let's just eyeball this. Let's go ahead and put in what I say was 3, 1. Okay, so there's that guy. Clearly that's a row vector. So what I'm going to want to do is go boom, boom, boom. Oh, fiddle faddle. Here we grab this dude. Check it out. So there, guy, transpose. Oh, fart. I'm going to mess this up if I'm not careful. There's your denominator, yes? Okay, now why is that backwards? Because I put that in as a row vector and I'm an idiot. Okay, that's why. Okay, so pay attention. When that formula gave that to you, that gave it to you as a column vector. So let's try that again. Now you know what's going to happen because we know that we are, oh, you fiddle faddle. We know what's going to happen here. We know that we're, oh, damn it. Just stop talking, Jay. Just stop talking. Holy buckets. Oh, darn it, you did it again, you jackass. All right, I think we got it this time, friends. Holy buckets. All right, so we're taking that guy right there, okay, times this guy, which is the transpose. Okay, there's your numerator. And then, of course, divide by 10, or if you prefer, times 0.1. Boom. There's your projection matrix. Okay. Now I know what you're thinking. Can I do this all in one fell swoop? That is, could I do a rotation, then a projection, then another rotation? Absolutely. So you're like, wait, show me what you mean. Oh, okay. So, yeah, I don't know. Let's do another one here. Oops, come back. Okay, so let's. Oh, I know what I got to do the first time. The first time I did this. So I just want to make sure it's clear. So the very first time I did it, I had. Just want to make sure this is clear for all of us. So what I did with over here is I took all this like so, and you're like, but Jay couldn't have done it all at one shot. And the answer is yes. Could I have taken the rotation matrix times the projection matrix times the rotation matrix times my vector? And the answer is yes. But then what is this times this times this? It turns out for this particular problem, it was negative negative 0.49, no, negative 0.49. Well, negative, actually, it was negative 0.5. Times my original function, which was 3, 2. And if you do that, what you will see is that I did it up here somewhere on this calculator earlier. I forgot to show that to you. I felt bad. It's right there. No. Up here further, ding dong. Nope, I deleted it. Awesome. Idiot. All right, so you know what we're looking for? We're looking for negative 2.5, comma 2.5. So let's check this out. You're gonna go dot dot 5, comma. Oops, we doing comma negative 0.5 semicolon 0.5 comma. Darn it, 0.5 times negative 2.5 comma 2.5. That's the gist of it. In other words, can you put, in this case, 3 matrices together by multiplication? And you can use one that will do all 3 things. That is, in this case, it took a vector, it rotated it 45 degrees, then it projected it, then it rotated it 45 more degrees. Absolutely. Okay? Let's do something different. So let's do this. Start with the vector. This guy here. Let's rotate 60 degrees clockwise. Pay attention to that. That means negative 60. Okay, and then while we're here, let's go ahead then and then project onto the vector 3, negative 1. And then let's well, what should I do? Oh, I guess, well, then let's project, after that, let's project onto the y-axis. Okay, that sounds like fun. Let's do it. Okay, so again, if you rotate 60 degrees clockwise, remember that's the cosine of negative 60, negative sine of negative 60, the sine of negative 60, and the cosine of negative 60. Okay, and then to that, we're going to use the projection matrix. Now I'm going to have to actually do this one. I feel like that's pretty similar to the one we just did a minute ago, so let's go ahead and do it. 3, negative 1, 3, negative 1 over 10. So that's going to be 9, negative 3, negative 3, 1, decimal, 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 decimal. Yay. And then then let's project onto the y-axis. So to project onto the y-axis, it's the same one we did earlier. Okay. Now, if I do this all in one fell swoop, and remember, it's important, it goes in this order. I mean, yes, we start here, and we work that way, but when you multiply, you got to go in order this way because for multiplication, it's not commutative. In other words, you get this answer first, and then you would times it by this fella, and then you would times the answer by that guy. So when you put them in order, it has to go this one, and then it left from left to right. Let's see what happens here. Now what? That mess right there, whatever that is. Now, we said we wanted to start with the vector -1, 2. So let's think about this for a minute. It's going to rotate it over here like 60 degrees, whatever. We're going to project onto this guy, right? So it's going to come straight down like this, dot, 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 dot. And we're going to come over to here, so it's just going to be whatever that y is. It's going to be comma 0, some comma negative something or another. Let's see if that's right. There you go. There you go. Okay, so that's the game. So this matrix right here that you got for an answer, that thing right there, will do the same thing in one fell swoop as doing the other three individually. I hope that helps.